little bot, little teeny one, and the model regenerates. Middle bot, it's like this. And then big bot was a spicier, this big thing. 3 giveaways, and this is a magnet viewer film, the green part. So this is a pile of magnets, and then if we put the film in front of it, we can actually look at the magnetic field. Okay, so here's a magnet, and this is what the film looks like.
Wait, so what's the output of what you would build in Rapid Harness?
This drawing. So this is like what you would actually release to a production vendor to make the harness.
To make your harness for you. Okay.
Yeah.
That's also less work.
Yes. Yeah. We can start.
All right. So for today's session, we were going to do a little MCAD, yeah?
Yes. Yeah. So you are the champion.
Okay. All right. So we'll unshape it up a little bit. So let me start this presentation. Share screen. Yakbot. Okay. Can you see the tab and everything now?
It's the text is a bit small.
Oh. Okay. Well, I like to have real estate, but I could.
Okay.
Here, let's try that. If you want to see what's happening. Okay. Cool. Is that better?
Yeah.
Okay, great. So, yeah. I haven't opened the model in a minute. Let's look at where we were at. So I think last we left off, this is just kind of like a volumetric study, just really basic product concept and blocked out volumes. We made the model configurable, which is kind of cool. We used a little on-shape configurable features situation, and we had a named variable, which is like the solar panel width. And then the model is currently built around the solar panel dimensions. So if we make this sort of like little bot, little teeny one, and the model regenerates, middle bot, it's like this. And then big bot was a spicier, this big thing here. So yeah, what I think would be good today in terms of next steps, we have identified some core components, and I think actually ingesting those into the model would be a good exercise. So it might be a little bit boring, but I'm going to start just by trying to pull in some of the key components for volumetric purposes and go from there. So the first thing I'm going to do is actually pull in the drive motors. I know we didn't finalize a selection necessarily, but what I'd like to do just for the sake of time and momentum is pull in these worm motors, these JGY worm motors here. Does the stream show my camera as well? I think
yep.
Right. Yeah.
JGY worm.
Yeah.
Motors.
So they come in like all kinds of different gear ratios, which is nice.
Mm-hmm.
And they're pretty common. The ones that I got in particular have a feature which isn't everywhere. So, standard gearbox and then brushed DC motor. But what it has is an encoder on the back. So this is really a nice feature. So this is actually a magnetized ring. And here, if you want, I could grab my magnet viewer film real quick. See here. I have. Have you guys used the magnet viewer film before?
I don't think so.
No.
You haven't seen this stuff? Yeah, so this is actually this was a giveaway at a trade show. I have some other film somewhere deeper in the mess, but this is actually like one of their free giveaways, and this is magnet viewer film, the green part. So this is a pile of magnets, And then if we put the film in front of it, we can actually look at the magnetic field. It's maybe here. Let me get a different magnet. It shows it better. Maybe this would be better. Yeah. Okay. So you see how you can actually see the magnetic field in the film. If we look at this rotor that's round, we're going to see kind of an array of poles. You see that?
It's vaguely
Yeah.
visible. Yeah, some like dots.
It's dots around the ring. Or
Yeah. So this is a multi-pole magnet, this little black cylinder. And that's maybe if I go on this way, it's easier to see. See how there's like multiple little segments. So the point is, this is actually like this little cylinder is like it has 64 I think it's 64 magnetic poles. We could count them with the film, if we actually were to sit here and measure it. But this is actually a little encoder. And then so you have a multi-pole magnet and then 2 Hall encoders, and that's it. So anyway, that's just like when you are buying these motors, you got to.
So how does that thing work? That viewer?
Oh, it has like little Let me see if I can find a better one real quick, just because it's a lot better. Yeah. Okay. Here's my other film. Okay. This will be a lot better. I'm sorry. This is my actual film, not the free giveaway. Okay. This should be a lot easier to see. Okay. So here's a magnet, and this is what the film looks like. So you can actually kind of visualize the magnetic field.
So there is some metallic content inside that film, maybe, right?
Yeah. So there's like little beads.
Yeah. Okay.
And they move either forward or backwards in the little pockets.
Okay.
Yeah. But I'm sure you could look up like magnetic viewing film.
Yeah.
So if we have this here.
Why didn't every physics teacher I
look at
ever had have one of these?
See that?
Yeah. Now it's much more clear. Yeah.
Huh.
Yeah.
Interesting. Yeah.
So this way you can actually count how many poles they have.
Okay.
Yeah. So somebody could take a screenshot of the cast and tell me how many poles there are in this particular part.
We're getting a little bit of a reflection.
A reflection, yeah. So it's not, but we got the idea. Yeah.
Yep. So that's that. But when you're just like checking stuff to see if there's a magnet, like a really good example is on a I don't have my AirPods, but like if you have an AirPods case and you want to know its secrets, just get some of this and put it over the AirPods or a computer. Like wow, I'm looking at this computer right now. There's so many magnets. They're literally all over the place in this computer. Yeah, so it's just fun to like take this and look where everything is. So to summarize though, these worm gear motors have the encoders on the back. They're not particularly high resolution, but with the gear reduction, it can be pretty high. So somebody can do the math, it's like encoder counts multiplied by the gearbox reduction, and then on the output of the wheel itself, we'll know how many clicks we have per rotation, and then we can take the circumference of the wheel and divide that by the number of clicks, and we know linear distance per click to kind of like have an estimate of where we are. Yeah, so let me see if I can find the motor. This is like if anybody wants to help with the step file hunt for this motor, that'd be great, because it's like probably going to be a little bit annoying to find.
Do you have numbers on what exactly that one is? Like I found like a JGY 370, but that's a different encoder.
Can you see just the, like when I'm changing my windows, can you see that? Or is it only the on-shape tab?
No, I see the on-shape.
Okay.
Yeah,
let me try to share a whole window. Okay, you should now be able to see multiple tabs, yeah?
Yeah.
There we go. Yep.
Yeah, okay. So what we're looking for is a step file. That's the most common CAD interchange format. And it looks like some very kind person modeled it and put it on the internet. So we will just use this. GrabCAD is a good reference point for a lot of these. There's 2 people that uploaded models. This one looks to be a bit more accurate, has more downloads. Let's see if this is this looks like what I'm gonna pull down.
Yeah, for what it's worth, this is the first thing that came up when I Googled for it. So
Cool. Yeah, okay, cool. So we'll download this. Oh, I gotta log. Oh my god. Let's see. This one. Okay, so with non-shape, it's pretty easy to just ingest parts. So we're gonna ingest this. Yeah, we'll ingest that step file, and we should have a nice model. Okay, great. Whenever I import a model like this, I have trust issues with models from the internet, even from models from vendors themselves. So it's always good if you have the real hardware to check it. I'll be right back. I'm gonna double check. I'm gonna get my calipers. We'll double check some dimensions. Okay. So we'll measure some key dimensions here just to make sure for our volumetric study it's accurate. So let's do this face to this face, 32. I'll get my calipers. I say 32. This face to this face, 46. Also accurate.
No, where are you looking at the dimensions?
Oh, sorry. So when I click 2 faces,
Okay.
down here on the lower right hand side, lower right, this right here,
Okay.
parallel distance, yeah. Onshape does give you that info just like at a glance. If you want to have more measurement info, you can do this, and it gives you a bunch more information.
Okay.
Yeah. So we need to know the bolt face to the furthest most extent. So the parallel distance is 24 and a half. See if I can also measure that. Yeah, checks out. Okay, so one thing that is different about this model from the motor I'm holding is it has the encoder on the back. Because again, the encoder is not always the option. So this distance is wrong. So this shaft end in the model is 80.8, and in the actual part is 85. So what I will do is make a version, because we just imported this, and if I want to roll it back, it'll be really easy. And then I'm just going to model in effectively this additional volume that we need to have. So I'm going to actually model it off of this space here, and we'll add the little circuit board. So we'll do convert. Then we'll extrude that 1.6 millimeters. Okay. Because the PCB thickness is about 1.6. Yeah, 1.7. Okay. And then we will also move this face. So it was 80.8, and then it needs to be 85 and a half. So 85 and a half. That's like 4.8 millimeters. So we'll do a move face. And we'll take this shaft and make it longer by 4.8 mm. Okay, so now if we measure this, 85.6, and I measured 85.5, so that looks good. the chamfer didn't get moved. So we want to translate this, not extend. And we'll make this face. That's correct. We want to keep that chamfer. Okay, very good. And then just volumetrically, you know, here I can also add, it's like real quick. It's usually very important to add the connector. So let me really quickly add this connector. It's at a 45 degree angle. It's 14 by 8. So we will do a offset rectangle like this. And this is 14 and this is 8. And then we need to use the center point of this circle to reference a 45 degree angle. Make that a reference geometry. Okay, so this is going to be 45. We also want to center it this, and then we will define this to go through the center point. And I'm just using a lot of hotkeys to be clear. Like if you're not seeing things happening, it's just because I'm pressing buttons.
What does Onshape call those dashed lines? Are those construction lines?
They use this one. Yeah, construction. The hotkey is Q.
Okay.
Yeah. So that's the connector I just added in because that's kind of like a strong consideration for our volumetric study in terms of the bounds. And then I'm also going to add in what's the diameter of this little guy here? This is about 14. Okay, so now we can extrude these things. So the first one will be this. This is like a feature that should have been in the product for a long time, but they just added as offset. So you'll notice right now I'm starting an extrusion off of a plane up here, but then I needed this gap to be accurate to the actual physical way it looks. Also, the motor tab location is different on this downloaded model versus the real thing. So this interference we're encountering is not present. But again, this volumetric study is primarily concerned with volume, like overall boundaries to the rest of the robot. So like even this level of fidelity that I'm adding right now would be considered by overkill, depending on kind of like the level of fidelity of the study we're doing. I just kind of want to go for it, so I'm just going to model this all in right now. Mainly the connector is the thing, but usually you would do let's make a version. Usually if you were just doing an overall like super rough thing, we would have just done this where we extrude this further like that and call it a day. Like that was what you would use for the volume reference, but this is a much more accurate model, and it has the connector, which is tricky because if we look at this thing from the end, that connector hangs out.
Yeah.
So that's actually an important thing to consider.
And we're also going to have to plug a wire into it. So nice to
correct.
know that there's room.
Correct. Yeah. I mean, wires are a whole thing. Like, yeah, that's in designing harnesses. That's a whole thing. So, like for instance, if we do add a wire into this model, just for giggles, so we do this, and then we make a pattern. I take this and make like this particular product has 6 conductors. That's not 25 millimeters. We want like a 1.2 mm spacing. We want to flip the direction and we want 6. Okay. Actually, the spacing is much higher. Oh, this is a I think it's a 2 millimeter pitch. Yeah. Okay. So, you know, we can add this in there. It's funny. I downloaded a model the other day. Unfortunately, I can't share it, but it I downloaded a model from a vendor the other day, and it was almost like somebody wanted to do a little. So they like modeled a wire, but it was all bent and organic for no reason. It was like a little sculptural wire that they added to the harness, because usually it looks like this, where you just have a stub. But anyway, it was funny. It just shows to me that there's no standardized way to communicate wire harnesses. And this is like an ongoing issue. People use this tool called Rapid Harness a lot. So this is like the number one thing we have to make wire harnesses. That's probably, some people would probably take issue with me saying that, but there are a lot of CAD tools that have a wire harness like extension or option. But if you're not in the ecosystem of a particular MCAD tool, you won't get it. And then Rapid Harness is, because the thing about Rapid Harness is it's I think, is it web based? Yeah, it's oh no, it is a desktop based thing, but I think it's a standalone application. It's not just like a SolidWorks plugin, so that makes it neutral between tools, which is an important point. Anyway,
Wait, so what's the output of what you would build in Rapid Harness?
these this drawing. So this is like what you would actually release to a production vendor to make the harness.
To make your harness for you. Okay.
Yeah, yeah. So they would have something that usually literally looks like this. It's yeah, like, because you actually have to cut everything to length and like add connectors to it.
I see.
Yeah, there we go. Okay, that's a good example. So this is like, if you're making a low quantity and you're building prototypes and humans are making it, you would have a jig like this to actually run the correct length and crimp the wires on and put the connector on and all that stuff. Yeah, but you need a drawing. Look at that. you need a drawing, right, to like reference to do that. And yeah, so that's ultimately the output. Because I make drawings like this in Onshape, but it's hell because you have to like manually define the tables and manually fill them in and manually check them. Versus Rapid Harness, you can kind of like define things and it generates it. And so like if you're using SolidWorks, they have like a what do they call it? It's like harness routing. So they have like an extension. You give them extra money, and then you can like route wires in 3D, which is nice. But the really nice thing is it can then help you automatically generate drawings, because it's the drawings and like going from what we're defining here to an actually error corrected drawing that's important. Because the thing is, it's like really easy to make errors if you're manually populating these tables.
So how is this used on the shop floor or the production?
This is like, this is ultimately the document that controls the product that's being delivered. So it's like, this is the spec.
Okay.
Yeah.
So those individual connectors at the end are potentially just like off the shelf, or hopefully an off the shelf thing, and it's just all the sizes and the number of conductors and where they all route to.
Well, correct. So, just to go over this, on the upper left, we have the bill of materials. This specifies the part number for each and every like wire in the harness, covering on the wire, the connector that's at the end of the wire. Every single part is defined down to each individual wire. And then you have on each termination the color of the wire and where it goes on the pin of the connector itself, which is again specified in the bill of materials. So this specifies every single part you have to buy to then put on the nails, and then how to connect them in the end product. And this obviously doesn't have like more complicated things. Will have more going on in testing procedures, but this is like kind of what you need to give somebody to tell them what to make you. It has like the distance of the wire and the kind of wire and how to connect the wires. But it's
But this is not fed into an automated system, right? Some human reads it.
Correct. Yeah.
It's not the same as like PCB manufacturing, I guess.
PCB manufacturing is also very manual. Like all of this is manual. Like manufacturing, like reviewing is manual. Like, the products like cell phones and stuff, it's rooms of people manually reviewing things. Like it's very manual. But anyway, we had to manually update this model.
Well, I assume what Anuraj meant was more like there isn't a harness printer that you can upload a CAD file to.
Absolutely not.
Yeah.
Absolutely not. No, harnesses are, especially to my knowledge, are a very unautomated thing. Very unautomated. Like there are, there's like equipment that helps. Like so there are like machines. You can get these for not much money. Like this is a machine that will automatically cut a wire to length and strip the ends to length. So like put a spool on the end, and then you tell it to make me 100 wires that are a foot long with a 1-inch strip on both sides, and it'll just spit those out. So there's equipment that does stuff like that, and then there's equipment that like wraps. Yeah. So you have I actually posted a video of one of these machines on LinkedIn a while ago, but it like has a tape and it wraps the roll of tape around the harness, because this is like most harnesses are wrapped. Yeah. Like if you open up your car and you look in your car, you'll see this tape everywhere, and it's all wrapped up, and you have to have a machine that like wraps the tape around the harness. But no, there really isn't a machine that will just like 3D print you a harness. Like it's not a thing. And harnesses are really, really hard. Same thing with crimping. Like there's automatic crimpers, but yeah, a lot of this stuff is just people making things. Anyway, okay, so back to this guy. So we got this motor now, which is good. Let me make a version. So I like to organize this COTS. So this is commercial off-the-shelf components. And so we will have the COTS folder of models that are off-the-shelf referenced here. I would say that these are sort of concepts. So I'm going to add these to a folder called Rover Concepts. Then the actual top-level assembly, we might pull in here. I'll just duplicate this and I'll make a separate assembly. Wait, did the duplication actually get rid of the...
What happened to the tail?
Oh, the tail's gone because there was a regeneration error for the little robot. Yeah, see, this guy's unhappy. The extrude forward is not happy. No, the thing that I'm looking at right now is these are all configured to a particular configuration. So I pulled them into the assembly in a particular configuration, but I wanted them to be a different configuration. So I just updated all of them at once. So now it's a middle robot. Yeah, so at a high level non-shape, here's something to go over. Yeah, let me delete this. Duplicate this. And then we'll say... this will be the top level assembly, and we'll use this as the working model to actually do things in. Here you go. Okay, so one thing you'll notice that I'm not going to do. So if I were to add this model right now and I click this, it's going to add a bunch of parts that are all part of that motor. We don't want that. We want the motor to be one logical element, and also because we look at the bill of materials, we do not want all these things to be like the motor should be one element. It should not be like multiple things. So the way we're going to get around that in on-shape, this is on-shape specific information I'm about to provide. So we're going to select all these parts, and we're going to do composite part. And what that will do is it'll give us this element down here that is one logical part in terms of how on-shape treats it, but it still maintains the color and that there are multiple bodies, if that makes sense. So just stick with me for a moment. So we're gonna delete all these separate parts, and then we'll insert that composite. So we have to select composite part here, and we'll add this. It's also called composite part 1. That's kind of a lame name. Maybe we should update it to. Oh my God, there it is. Okay, this is. Okay. We now have a motor in the model. This is the middle rover, if I recall correctly, and we don't need that shaft anymore. So when you're just blocking out something like this, I do a lot of just freehand dragging, just because if we started to add mates and stuff to this, like the issue is fundamentally we don't have any geometry. We haven't designed the system yet to create holes and things to assemble the things together with logical mates. So I'm just going to drag things around and get them into the approximate location. And then once we kind of like that blocked out location, we can start to actually add the features into the model. In the case of the motor, I might cheat a little bit. I might cheat just a little bit. So, because we do know about approximately where we want it to be. The thing we do know is that we want it to be referenced off of the center of the robot. So just to keep things simple, I will, in fact, add a constraint. And this is temporary, if that makes sense. It's a temporary constraint because we would usually add a constraint between the motor and the thing that the motor is mounting to instead of the origin of the assembly. But I'm going to add it to the origin of the assembly right now, just so that I can define an offset, and everything is lined up. But generally, so I feel like I'm saying conflicting things. Generally, for initially blocking stuff out, just dragging it around is cleanest and most efficient. Okay, so this is an example of where the motor could be mounted in the final assembly. And we can start to do things like section views and look for interferences.
So now the motor is fitting exactly to that box. So was that box initially designed with the motor in mind?
So right now, the motor is referenced off of the assembly itself. So this assembly has an origin.
Okay.
And we've constrained this using a parameter. So if we look at this fastened mate, we typed in 150 mm from the tip of this shaft to the origin. Actually, we don't want it to be the end of the shaft. We want it to be here, because this is where it'll be bolting onto the side of the housing. Okay. So yeah, this is now defined in space. These parts are completely floating because this is the actual plastic that we will flow around the components, if that makes sense.
Okay.
Yeah. So it's like we know where things need to go, sort of. So we're going to block them out as if we were physically laying them out on a table. And then we will just flow the plastic around them.
Was anything else constrained to the origin like that? Like, are the wheels on an axis?
No.
Yeah. Okay. Okay.
Yeah. Currently, no. It's again, this is all just like initially placing it.
Yeah.
Yeah. So like the way you would, like, if I did want to make sure I didn't accidentally drag anything, I'd select all of these. I would group. So do this group, and then we'd fix one of them. Okay, so now this is a group of things that are glued together as far as the MCAD tool is concerned. Other parts fashioned. Oh, did I accidentally? Okay, well, I over-constrained something somewhere. Unfix. Not sure why it's throwing that error, but at any rate, the group binds everything together as if it were like, cast in amber, and then the fixing will just say, hey, this part is not allowed to move relative to the origin at any point. And so we're fully constrained. Okay, so you'll be asking, why am I adding a mate connector? This is another on-shape thing. I almost always add mate connectors to facilitate section views, because otherwise section views in on-shape are sort of cumbersome. So I'm going to do a XZ plane mate connector, and this will become evident Y. I usually rename these two. So this is XZ and this is XY.
And a mate connector is more typically used for how to actually couple two components together, or
yes, mate connectors actually serve a bunch of different purposes in Onshape. It's a very much like an Onshape specific innovation. Yes, like the canonical use is to form mates. What I'm doing right now is I'm defining a plane, because in SolidWorks assemblies do have planes. In Onshape, the only thing that you get when you create a new assembly, so like let's just do it. We'll create a blank assembly. The only thing that's in here right now is an origin. That's it. That's all you get. So if you want to do a section view, the origin provides inadequate information. Because like in Onshape, normally, if I wanted to do a section view, I'd have to select a thing. So I could select the cylindrical face as an example, and it would do a section view.
Are there construction planes? Like I think Fusion 360 does that.
Not in assemblies. That's only when you're designing modeling parts. So this is my point. If I want to actually do a section view, I can use this XZ mate connector as a plane reference. So it acts as if it were a plane.
Yeah.
So, and it even, like, when you click the mate connector, I think it's kind of a weird thing. I should probably push back on them to like name it something else, but this defines a plane as far as like section views are concerned in assemblies. So I'm almost always adding these two anytime I'm in a new assembly, just to facilitate section views, which is an extremely common thing to do. But anyway, so we're in the section view and we can start to look at this. So it's very clear that we need a little bit more room. And then this encoder adds a big curveball. So we need quite a lot more room, potentially. What I'm going to do right now is use in-context editing. So this is, there's a few different ways to model things, but before I do that, though, I will add another motor. We need to do assembly circular pattern. I'm going to add this. You might be asking, why am I using a circular pattern? The reason is Onshape doesn't have mirror in assemblies, which is like people get very upset about that when they're coming from SolidWorks, because SolidWorks does have the concept of mirrored assemblies. I understand if you're designing a new CAD system as as Onshape did, why you wouldn't do that though, because when you're mirroring a part in an assembly, there's some ambiguity there and complexity that the different CAD tools deal with in different ways. So this is my kind of hack to do a mirror, is I used a circular pattern rotated around this mate connector that then produces my desired result, which is to have two motors that are mounted into the frame on either side, but in the correct position. So these are fully defined. They are exactly in the position that I want them in, and then we can move forward. But that's just like another kind of Onshape gotcha that in SolidWorks I would have used assembly mirror, and it would have asked me to disambiguate which orientation of the part I wanted the part in, which is buggy and weird in its own way.
Sorry, and that's just to specify whether the part itself is a mirror image of a mirror image.
Exactly.
Okay.
So it's like, do I want to mirror the same part on the other side of the assembly, or do I want to literally mirror the part?
Right.
That's a hard question to answer if you just run mirror command in an assembly. Because like if you
circular
want
pattern kind of makes a lot of sense.
right,
to
exactly,
me,
right,
yeah.
right. The issue with circular pattern is if you don't have this main connector in exactly the place that you want it, it sucks. Because like imagine if we had this motor moved up, it's wrong. So like just real quick, if I take this and then I put it 50 mm up, well, that happened to be the right one. That happened to be the yeah. See what happens? Because like what I would want is the motor to be up here
Oh
on
yeah.
the upper part.
Yeah.
Yeah. So then you have to like add the meat connector in the right spot, and it's a mess. But yes, the disambiguating, do you want a mirror of the geometry, or do you want to put the same part mirrored in the assembly area? All the different CAD packages have different ways of mediating that issue. So there's a few things that come up immediately. We need more volume. These are also asymmetrical. So what we're going to do is, as I mentioned, we'll do an in-context edit. So we're actually editing the model of this part, which is in here. So we'll actually be directly editing this model, but from within the assembly, so that we can actually see the context of this part in the assembly without having to insert the motor into this model. Some people, and so there's a lot of different ways to do this, and people have different preferences and workflows, but just so you're aware, you can add parts into a part studio like this. So this is now in the part studio, but it is really cumbersome to move around because this is like you can't just drag it and move it. So I do not usually. I tend to go on the side of in context editing of assemblies as a top level design workflow, as opposed to like deriving stuff into other part studios. Does that make sense to everybody, or is that confusing?
I'm assuming that's because of when you import another part, it's just they have the same origin.
Correct. So, but it's like if you want to move it around because we're like assembling, what we're doing right now is we're like putting stuff out on a table and then like covering it in plastic. So we just want the things to be laid out so that we can cover them.
Yeah.
So like here we go. We're in context editing right now, so we can kind of see the parts, but then we're gonna edit the model in real time to flow around those parts, and we have the full power of section view and everything to evaluate the geometry, and we can also see how it's letting me select this line. We can actually reference this geometry out of the assembly itself into the part, which is very powerful.
I have several times in Fusion 360 confused myself because it's like, yeah, this is what's happening by default, and it's just visibility of certain components are there or not.
Yeah.
And sometimes it's like, why can't I click this face? And realizing that, oh, that's actually not the part that I'm editing. That's a different one.
Yeah.
Can get confusing.
So this is going to be driven. We'll free this up, and then this will be 300. Okay, so that's kind of the thing. We do have to make a choice though. So we can either make this really big. Oh, and I'm gonna break all of our little yeah, this is gonna break everything. But
You
that's
had
okay.
this like was it parametrically?
Yes. Yeah,
before?
I had it parametrically hooked up. Yeah.
Yeah.
Let's here. Because I want to kind of keep this as is. So I will make a concept master. Just in case somebody wants to go in here and check this out, I'm going to leave this in place so that that will work without having to go into the history, because you can always go back in time and look at stuff. But I'd like to keep it in the model for reference, or in the current working version for people to reference is what I'm saying. So we'll duplicate this one. This will now be the master model. Then we'll go back into the assembly, delete all of these parts, and reinsert them from the master model. And then we will update the config to medium as before, and we will repeat our in-context edit. Okay, so now I'll start ripping up all of the parametric modeling that was set up before. This is the key question we have to answer is, like, do we want the body of the rover to be symmetrical about the shafts of the wheels? Because if we do have to do that, the size of the rover is quite large. So this would be, what's 150 look like? And also just hand drag it. So we'll make this driven and hand drag this now. So if we do this, you see how in order to accommodate the motor, we have to make it symmetrical. So we could either do that, or we could just get rid of this constraint here. Oh, I actually did some, this is kind of complicated. I did a lot in here. Trying to look over my constraints.
You're on mute, Anurag.
I'm going to try to delete these constraints until I get.
So are we designing it so that even if it flips, it will keep moving, or is it like only upright?
I would suggest a flippable design. The biggest implication there is that that imposes symmetry, and that also imposes okay, so if we impose symmetry on the design, like we were talking about a downward facing camera, and that means we need to have symmetrical downward facing cameras, or a front facing camera with symmetrical like FOV, you know? So that adds.
We also have a solar panel.
We'd have to add 2 solar panels. Okay, here we go. So yeah, this is now free to drag. So this is kind of like the one option, and this is what did I do? I think I know what's going on. We're just gonna do a mirror real quick. Just keep this clean. Okay, so now, that's our, okay. Sorry, but the key question is, do we have a rover that looks like this, or a rover that looks like this?
What would be the implications of either of them?
I think if it's asymmetrical, we have the potential to balance it, or to shift weight into the rear.
We can always populate the volumetrically it would be symmetrical, but in terms of center of mass, it's where you load the weight. So we could always put the weight in the back either way. I think the biggest thing that I would question is if we do have a camera with a wide FOV, and if the camera is mounted on the front, we're going to have occlusion from the wheels. So this gives us no occlusion for a wide FOV camera. This occludes us by some amount, given a center-mounted camera. The other question is, will this robot ever flip over, right? This gets back into the symmetrical thing, because if it has to flip over, if it tried to flip over, this would dig into the ground if it was this far out. But this would have a lot of clearance.
But can we make some sort of protrusions from there so that the camera is a little forward, so that there is no occlusion by the wheels?
We certainly could have kind of like eye stalks, but I would suggest maximizing the simplicity. I would love for the whole shell of the robot to be 2 parts.
Okay.
Yeah, just to keep this thing as robust and as simple to produce as possible. Because it's like the wheel is 1 part, the body is 2 parts, and the tail is probably 1 part. So the whole robot is only 4 parts, 5 parts. I think this is what I would suggest. No need to make it symmetrical. So I think we can feel free from that constraint and independently drive these edges. I think these edges should be independently driven given the system requirements. So maybe this is kind of like a we could also look at the FOV real quick. I can add that in here just so we have like a reference. So that gives us, got to multiply it by 2. So that's 190. That's 150.
We may also be very quickly reaching a size that we can't print on a normal sized 3D printer.
Right now, the largest overall is 300, which is about it's about a foot. What is a typical?
Yeah, I was just trying to look at mine.
Prusa?
I think 21 centimeters is the smallest.
Yeah, it's I think 210 by 210 by something.
Yeah.
Well, what's a typical larger one?
Yeah, let me see. Because they just produced an XL one, didn't they?
Sure. Yeah, that one.
The Prusa XL would be 360.
Okay, Bamboo Lab is 250. Absolute max. What's the smaller Prusa?
It was 210.
Okay. What does that look like? That's not the right constraint. I'm gonna midpoint that one. That makes more sense. Okay.
But Anycubic has 400 into 400 into 450 mm. It's like their higher end one.
Okay, so that's what that looks like. Let's see if this rebuilds. So that's like the big part on a preset printer. Like
So
another
what's the
decision,
dimension here?
200.
Okay.
Yeah. So if we want to see what the motor looks like. So the motor would be mated 100 mm away, not 200. Yeah, we could do that. Yeah, it might be good to add some more parts in here real quick. Are we gonna do an RPi? Is that kind of the plan?
I feel like that's a big stretch goal. And we should probably do the other parts first. The whatever our PCB ends up being.
Oh, but I just mean for the volumetric study, like we have to have it. So, yeah, I mean, I don't think I already have a RPi in my library somewhere. I also can't show my, yeah, I can't show that in the screen share.
What about batteries?
Oh yeah. Let me here. I'm gonna add some stuff in that I can't screen share as I navigate through my files. Because I do have batteries.
Oh, we are over time also. Not that I'm in a rush to be anywhere, but
Oh yeah, sorry. Was this good though? I mean I just do this all day.
this was
Yeah.
great. I loved it.
Yeah.
Like I just for better I'm just sitting here modeling.
But yeah, could you share the link to the model again? Because it's all in public, right?
For the RPi?
No, for the I don't know where the link for the YakBot project on Onshape was.
So like, how do we start like tinkering with the design you have?
Oh, I have this set to anyone with link. I don't have it public right now. I could make it public. Should I make it public or should we just start with the link for now?
Let's start with the link. Yeah.
Okay. So this is a document. Anybody should be able to open it up. Sorry, I should have posted that at the beginning of the stream.
I would have got distracted if I had that.
Okay.
Cool.
Yeah, I think to recap, there's a few things that came up because these are just like design decisions as we're going. So it's like, is inversion or flippability a hard no? Like we're not designing for that right now. And then the second thing is I do think there should be a better definition of whether or not we're going to be designing as a slave to the manufacturing capability. Because if we are adding this constraint that like whatever model of 3D printer somebody happens to have, it must be printable on like whatever. If that's a constraint, that's a constraint. Otherwise, we can loosen it up and use the service bureau, or say somebody buys like the big Creality and prints off of that. Yeah, so I think those are some good talking points that we came across. Yeah, otherwise we just need a complete ingestion of the off-the-shelf components and then just fill up the volume. And pretty straightforward. Do you want to keep doing the modeling next session, or should we go back to some of the part selection stuff?
I think this somewhat leads to part selection in a way too, but just like we've got some batteries here, so I'd like to continue this process, and unless we happen to have a great software demo, but I don't think we will. I think Eric mentioned he had
Something.
little Zephyr stuff to show.
Cool.
But we can,
right.
yeah, we can discuss that in Discord. But how, like, if I start doing something, can I fork this design in Onshape?
You can create a copy of for your own. I think.
Yeah, you can totally. If you, I don't. Wait, let me.
Did they call it forking?
They call it
This tells me it's view only.
Yeah, no. So okay, what I'll do is I'll make it public because that allows linking and copying and all this stuff. Do you? Yeah, because and that also that means you don't have to have a license to edit it. So I'm gonna do that right now. So I'll make this a public document. Let me just glance at this real quick.
Yeah.
Just need to make sure. Okay. Yeah, because I just have a lot of data in Onshape. Okay, I think this is good. Okay, so I'm going to make this public right now. Okay, it is now public. So that means anybody can do anything.
Yeah, sorry. I think you have to make it public for to be able to make a copy to edit. It still won't let us edit on the main document, but we can at least make a copy and edit it.
Yeah.
Yeah. Let me see. It's interesting. Yeah, so I can view, like, when you make it public, you can't. Oh, I'm not sharing anymore. So let me just show you so you can see. So this is the current config. And you can see it's now public. And like, so for instance, if I made it not public anymore, this would come back. But like when I make it public, it's just a button that goes public. Like I can't change any of the parameters. So I do think what we could do is if everybody has Onshape accounts, I can add you to become editors as well. And I think as long as it's public, you will, because everybody has an Onshape account, right? The free tier.
I have it. Yeah.
Yeah, I do.
Yeah. So I think if I add everybody into the document, you'll be able to edit it since it's public.
I wonder if it use up some of your team licenses. I don't know if that works though. I forgot.
I have 2 seats of professional, but they're all used. Yeah. But yeah, here, what should I? Can you guys send me your Onshape names?
Yeah.
Here, I probably. Okay.
It should work by email address. You should be able to add by email address, I think. Sort of.
Yeah. What I'll do to make this really easy. Well, okay. For now, I'll just add these emails manually, but I like to make teams and then share documents with teams. It makes it really cool. Okay.
Do you think it would be? And this is
I
just
think it's
wild
from
idea.
Anuraj. Okay, Anuraj, you should have it. Can you try it?
Just wait. Yeah, it's not saying that view anymore. That view only mode anymore. So I think, move things around.
Nice. Cool.
I think I moved something.
All right. You moved something.
Now revoke the access.
Okay, so here, I'm gonna undo. Well, it's whatever. Just make versions. That's all.
Okay.
I'm going to make a version right now. And then the thing I didn't do is merge this back into main. So I'm going to merge this into main so that main is fresh. Okay, main is fresh. I'm going to make a version in main, and that's what we'll stop for today.
Okay.
Awesome. Okay, so
Cool.
if y'all send me the emails, I can add you, and we can all collab in the same doc.
Okay.
All right, I've got to run. Cool. Was that a good session?
Yeah, actually, it was great. Yeah.
Yep.
Yeah, great. All right, cool. Catch you later. Thanks.
Thank you.
Bye.
So-